So in this video, we're going to talk about the SMILES notation. So the SMILES is the abbreviation of Simplified Molecular Input Line Entry System. So in short, it is called SMILES. So the SMILES notation is actually the 1D representation of a molecule. So it doesn't contain any information about the 3D coordinate. So the purpose of SMILES notation is that to save a molecular structure in a very simple form, like in a text. So on the right side, on the right bottom, so there is an example of the SMILES notation of a molecule. So SMILES notation of acetaminophen. So the molecule is represented as a text, as a 1D text. So it consists of various symbols representing atom, bond, and branches. Oops, there's a typo. Represents. So it does not show hydrogens. So the hydrogens are automatically attached based on the valence law. So let's look at how SMILES can be written for a molecule. So the atoms, first, so the basic principle of SMILES is that the atoms are represented by their own symbols, by their own atomic symbols, like carbon is written in C, and fluorine is written in F, and oxygen atom is written in O, and chlorine is written in Cl, and so on. And bond, how the bond informations are represented. So the bond is also simple, and the single bond is represented with this short dash, and the double bond is written with this equality symbol, and the triple bond is written with this sharp symbol, and the aromatic rings are generally written with this colon. But this single bond and aromatic bonds are not usually used. So all you have to memorize is that this double bond and triple bond. Then let's look at some examples. So if we write down methane, the methane is written as a CH4, right? In SMILES, as I said, so in SMILES we don't write hydrogens explicitly, so they are just written as a C. And if we look at propane, the propane is a chain molecule. If you write down them on a paper, then it would look like that. But as I have said before, it means that hydrogens are ignored, so only heavy atoms are kept. Then we can write it as a C-C-C, but usually dashes are also, single bonds are also omitted. So the propane is written like this, and chloroethane is written like this. So this, as I said, hydrogens are ignored and single bonds are ignored. Only atomic symbols are kept. Ethane, bromoethane. So let's look at bromoethane. In bromoethane, the hydrogens are erased, but the double bond is not omitted. As I said, only single bonds are omitted. So the double bond is kept, which is written as an equality symbol, and Br is left here. And if you look at acetylene, then they have a triple bond in the middle. So the triple bond is represented with a sharp symbol, and acetonitrile is also can be written like this, right? So the hydrogens are ignored, but the triple bond and nitrogen should be kept. So I think you can, from these examples, you can easily see how SMILES representations work. And another interesting point is that SMILES representation can represent branches. So as you must have learned from the organic chemistry class, so organic molecules usually have branches. So if you look at this 2-propanol, so the 2-propanol is a So propane is a chain molecule, but propanol, 2-propanol has a OH group at carbon number 2, right? So this is a branched molecule. So the basically branches are written in parentheses. So the parenthesis is this one, right? So if you look at this one, I mean, so just the simple propane is just a CCC, but in order to represent that, I mean, this O is a branched molecule, so that is put inside the parenthesis. And tertiary butanol is also written like this. So the CCC is written here, but this one is branched, and this OH group is also branched, and the branched groups are put inside parenthesis. And if you look at the isobutylic acid, then it has CCCO chain. Then we can say that we can think that these two groups are branched, right? We can assume that these are branches. And then if we write, I mean, this C corresponds to here. Okay, let's change the color. Here, so this C corresponds to the first C, and this C corresponds to this C. And if we think that, I mean, so the main chain goes to here, then this C corresponds to this C. Then what about this group? What about this group? This group is put into parentheses to represent that this one is a branched one. And also this one is a branched one. So this O is put inside the parenthesis, and this equal symbol is necessary to represent the double bond, and there is a O, right? So the branches are put into parenthesis. Also, branches can be nested. So if you look at this example, 3-isopropyl, 3-tert-butyl, 1-pentanol molecule, and yeah, so which is quite complicated. And so let's say that, I mean, so this is the main chain. Then we can say that this one is branched and this one is branched. But if you look at this way, this one and this one, if you look at this way, I mean, these ones are also branched, right? And if you look at one, if you choose one main line, I mean, this one is also branched, right? So let's look at this example. Then this C corresponds to here, this one corresponds to here, this one corresponds to here. Oh, then we have branches. Actually, this carbon has two branches. I mean, so one goes to here, one goes to here, right? And then let's go to here first. I mean, the bottom first. So this one, if you go to this line, if you follow this path, then the next C comes to here, and we have to represent that this one is branched, and this one is put into here, and this one goes to, and this C and this C are connected, right? So this one corresponds to here. And if we go to if we look at the upper group, then it also has, I mean, two. Let's say that so we can choose. I mean, actually we can choose any path. So this carbon corresponds to here, and this carbon corresponds to here, and these two carbons represent these branched carbons. And after that, again, I mean, so this main branch is written. So this C and this C are written here. Okay, so as you can see, the branches can be nested. So parenthesis can be put inside the parenthesis. So this is the meaning of nested. And also there's also another important fragments in organic chemistry are cyclic structures, right? Then how can you represent rings? So in Smiles representation, rings are represented by breaking one bond, and numbers are used to represent where cyclic bonds are formed. So for example, let's look at this cyclohexane. Okay, then as usual, hydrogens are omitted, and then this one is simplified like this, and then we assume that one bond is broken here, then the whole chain is like this, right? But actually there is a line, right? But we have to represent it as a chain, right? So we just artificially, we just assume that this is broken, right? Then it becomes a chain molecule, right? Like this chain molecule. Then if this one becomes a chain, then we can write down like this. C, 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 C. But actually there is a line, right? So in order to represent this line, we put number 1 and number 1 at the connected points, at two endpoints. Then this number 1 and this number 1 means that these two atoms are connected actually. So by doing this, they represent cyclic. They represent cyclic structure, right? So when you first write down as a Smiles, you assume that one line is broken, but in order to represent that actually they are connected, you put numbers. Then the same numbers are, the atoms with same numbers are actually connected. Okay, then let's look at some more examples. So if you look at this cyclic molecule, then as I told you, so we assume that one bond is broken. So we assume that this bond is broken. Then it becomes like this, right? But in order to represent that, so this ring should be closed like this. Then the number 1 and number 1 are put at both. So these atoms are represented as C1 and C1, right? As I told you, so this number 1 and number 1 are used to close the ring. Then it becomes a chain molecule, right? So it goes like this. Then let's say that this one follows this path A. Then we start from C, then the C1 comes after that, right? C1, and the double bond, single, 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 single. And we can write down these molecules. But we have to represent this branched bromine, Br, right? So the Br is put into the parenthesis, and we can write down like this. Another way of representing this molecule is that if we think that our main chain is like this, then this one is, we can assume that this one is branched, right? So if we follow this B path, then it starts with C, C1, C, C, Br, right? So these are main lines. But we can think that this part is branched, then this branched part is put into parentheses, and C1 is written and covered by parentheses, right? But C1 and C1 indicates that these two atoms are actually connected. So the ring is closed here. Ring should be closed between these two atoms. Okay? So the key point here is that, so the ring closure, so the rings are closed between two atoms with the same numbers, and also one molecule actually can be written in multiple Smiles, in multiple Smiles representations. Okay. Then let's look at the example of naphthalene. So the naphthalene can be written in several ways. So if we start from here and if you follow this line, and it is written like this, C1, CCC2, CCC2, C1. And these C2 and C1 are actually connected, right? Also, this can be written like this. If you think that this is the start, and if you go around this, then this atom, this carbon should be connected with this one and should be connected with this one, right? And then we can write it like this. I mean, C1, 2, and CCC, C1, C2, and so on. And also, you can start from here and it goes like this. So actually, naphthalene can be written in multiple ways. I mean, these all three are all okay. Actually, they are all valid representations. And there are more examples on the right side, right? I mean, so if you look at this example, or you can write this example. And here, actually, so we can write down, we can specify charges of charges of atoms. And if you want to specify charges, they are put into this, this bracket. And here, this parenthesis, not this parenthesis. And here the O minus, or here the N plus can be written like this. So take a look at these, examples more, and you will understand how this, SMILES representation works. And here are more examples. So in this example, it started from here and the cycle goes to here, right? Here, so it starts from here and cycle goes to here. And here it starts from here and cycle goes to here. And bromines are represented with parentheses. They are branching, right? Okay. So what are the general principle of generation of SMILES? How to generate, SMILES? First, ring structures. So let's say that we have molecule like this, A. First, so we assume that ring structures are assumed to be broken. So we have to break some point arbitrarily. So this is arbitrary. You can break any bond inside the ring. So let's say that these yellow lines are broken. So here, 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 here. So these let's assume that these bonds are broken. And then you put numbers. You put numbers 1, 1, 2, 2, 3, 3, 4, 4 to represent that these are actually connected, but we just assume that they're broken. The second step is we find the longest chain. So after breaking all these rings. So after this, so we find the longest chain. So which one is the longest chain on this molecule? So actually, if you follow this path, then it becomes the longest chain. So here on the C, the green line, so this green line represents the longest chain. Okay? And the other parts and other bonds connected to the longest chains are considered as branches. So this one, this one, this one, and this one, these groups are considered as branches. Okay. So in summary, we start from here and we end here, okay? Then how does it work? Then we start from N1, CC, CC, N, right? And it goes to C, okay? So this C corresponds to here. But this group should be represented as a branch. And this one also goes, and C after that, double C is represented here. And C, C, N. But this group should also put into a parenthesis, right? and this group branches, and this group is represented as also as a branch, and this group is also represented as branch, right? So as I said in the previous slide, so the multiple Smiles representations are possible for one molecule. So as I said, so you can break, so when you break the ring, especially when you break a cyclic structure, actually you can break here, or you can break here, and you can break here, and you can break here. So they are arbitrary. So there can be multiple Smiles representations for one molecule. And also we have to represent chirality. So then how the chirality is represented. So to represent chirality, we use at symbols, at one at symbol or two at symbols. And the key point of how to represent chirality is that the first atom is considered to be the center atom. Okay, so let's say that so this, we have this representation, and there is a chirality symbol, right? And the chirality is defined based on the following three atoms. So let's say that so this carbon so this carbon has a chirality, right? And this N is at the center. So if you rotate this molecule, then N is actually seen from, so if you look at this slide, then N should be actually here, and carbon should be behind it, right? So the N is here, and this, chiral carbon is here, and CF. And based on this order, NCF, based on this order, CF and C, CF and C, and this C corresponds to here, right? This C corresponds to here, this F corresponds to here. And based on the order of these molecules, so this at symbol is a counterclockwise. So as if you write this at symbol, then it goes to counterclockwise, right? And two at symbols mean clockwise, okay? So, okay, let's take a look again. So this one is the chiral center of this molecule, right? And this carbon corresponds to this one. So this one becomes the first one. And this fluorine becomes the second one. And this carbon corresponds to this one. This one becomes the third. So let's say that, if you look at this molecule from the from this direction, then this one becomes number 1, number 2, and number 3. Then it rotates like this, right? This is a counterclockwise. So that's why this one becomes a counterclockwise, this carbon. And 2 at symbols means clockwise. So think about these examples, okay? And also another thing we should specify when we draw a molecule is that when we represent a molecule is how we should specify cis and trans, okay? And cis and trans are actually easy. So that let's say that we have these two isomers, and this one is a trans molecule and this one is a cis molecule, and the trans is represented with these two slashes. And the cis molecule is represented with this, this slash and this backslash, two different slashes. Okay, so if they are the same direction, they are the same slashes, then they are trans. If they are different, then they are cis molecules. And as I showed you in the previous slide, and so we can also specify charges. Charges can be written inside the bracket. This is a proton, this is a hydroxyl ion, this is a hydronium ion, and this is ammonium ion, and so on. So yeah, so far so we have learned about the definition of Smiles representation. So the Smiles is a very popular notation, but the thing is that this could be advantage or disadvantage, but Smiles, one molecule, as I told you, can have multiple Smiles. Smiles 1 and Smiles 2 and so on. So in order to fix this, in order to make a unique text representation of molecule, actually IUPAC created a new notation called Intial Notation. So this, you read this as an Intial. So with this Intial Notation, the key is unique, and also it can contain more information. But the problem is that it is harder to read than Smiles. So if you look at the example of ethanol, so the standard Intial key is written like this, so which is not so intuitive, right? So things become more complex. So if you look at this, ascorbic acid, then the Intial key becomes much more complicated, right? So these ones are much more complicated. So the Intial keys it has some advantages, but Intial keys are not as popular as Smiles representation. Okay, so in this class, in this video, so we have learned about the Smiles representation. Since, as I told you, the Smiles representation is very widely used, so it is better to know about the Smiles representation and it would be better to know how to convert one molecule to a Smiles, or converting Smiles to a molecular structure. Okay, so in the next video, so we're going to talk about the popular chemical databases, and after that, so we're going to, practice how to download information from the databases. Okay, and see you in the next video.